All right. Well, I hope everybody did have a nice couple of weeks break by the end of QA and getting back now into clinic and to the full swing of classes. Remind me again, my guess is you guys have one other class, obviously, besides clinic. Is that right? Okay. All good, Chris. So this particular class is something that, for a little bit of historic sake, was something that we had created. I was really this was one of my two babies that developed long ago, and it was actually the original course was called electron beam therapy. And it was funny because it was right around the time, well, the University of Washington has a neutron facility and had a dosimetrist there, Sharon Hummel, who was very well known to the radiation therapy community in the Seattle area, was kind enough to come out and do a couple of lectures on neutrons. And all the while, we were also in this community putting in a proton center. So there was a lot of talk, a lot of focus, a lot of discussion on protons. And I don't know at what point, I think maybe just the last class before you was the first one where the formal name of the class actually got updated to particle beam. But lo and behold, it was, for a long time, treated as just electrons, but we would talk about everything ons, whether it be phot, elect, prot. There's just a lot of ons. All right, so let's have a look and see what y'all have over in Canvas. So this week we have, you should have access to the syllabus, so we can take a look at that. There are a couple of mandated things that have changed from the college that I want to make sure I draw your attention to. So this is dosimetry 331. This is my contact information. All that is good. However, I wouldn't try to call, just stick with the cell phone work number. I'm only at downtown 2 days a week. The other days I'm at the other sites, so it's probably just as easy to reach me on the cell phone. I will try this quarter to continue to be available Wednesdays from 5 to 6, just as kind of here to answer anybody's questions. I will put out a caveat that most likely I'm going to be losing the Wednesday off here in the not too distant future, so my schedule might change a little bit, but I am committed to making any and all necessary. If you need to talk about anything related to the course or otherwise, I am happy to move all things mountainous to accommodate. So in terms of this particular course, what are we going to be talking about? Well, as I said, we're going to be talking about a lot of ons. And obviously, there are some things that we have direct need to know just for day-to-day clinical stuff. Does that mean you're centered? So we actually, I have hired 2 former students in dosimetry over the last year. So I am always partial to students and people that I have worked with and trained. One of them was our student in the clinic, and the other one was graduated a couple years ago. But yeah, as far as if I could, and nothing taken away from any other school or program, and the dosimetrists we have are all rock stars. So I'm hoping we don't have openings, but rest assured, I am very partial to people that I have worked with. So if y'all are from a different area and want to move to Seattle, keep a line open, because things happen, things move. So you never know where things come from. But specifically to this particular class, so we're going to talk a lot about electron beams, because go figure, we treat with electron beams in the clinic. Does anybody not do electrons? I guess there's potentially a clinic out there too that just do photon treatment, if you're like just a Tomo site or a CyberKnife or something. But I believe all of you have access to those negatively charged particles. When we get into what I not find funny, but just kind of is the curriculum guide surrounding particle beams and whatnot have some clinical facets to it. Like, if you work in a proton center or can gain access to one, it would be great if you could do plans on protons. Well, while there are many more proton facilities, it seems like each and every year, they're still not so easy to find the way that a standard photon electron, more conventional treatment facility is. So a majority of you, as will be the case from here on out, will not have access directly to a proton facility. But that does not mean that we can't discuss a lot of things proton, such that, because there are some foundational things that you need to understand, not only for your boards, but just in a practical sense. And it's nice, these things all kind of tie in a little bit together. But with respect to some of the things we're going to be talking about with electrons, the more clinical things like therapeutic range, practical range, what happens with Dmax, any sort of changes in fluence of the electron beam, if we add bolus, Sarabin blocks, isodose patterns, MU settings, super easy, by the way. There's only a couple ways to do a calc for an electron. So good news for you, the hard part's over in terms of calculation. And anything that I've thrown at you before with photons, you're going to really think that electrons are really easy. We are going to talk a fair amount about the clinical side from the standpoint. It's not uncommon for physicians to come back and seek the counsel of dosimetry to assess what energy, what Dmax, what field size, things like that. So it's important that you have an understanding of what happens across the range of electron energies, field sizes, over and across various clinical situations. What happens when we match fields, overlap, when we have separation? What happens when we add photons next to electrons? All those things are very important. And then there's two very specific kind of specialized procedures with respect to these fun little things, electron arc and total skin electron therapy. Electron arc is still used in isolated cases in very academic-based centers. Total skin is still done, probably in the same magnitude of not as often, but academic centers nonetheless. Okay, and then obviously all this same kind of stuff with protons and all that good stuff. So this quarter, you'll have some quizzes, some homework, and some journal clubs, a total of 8 for 120 points. Participation, you'll have a midterm, and then you're going to have a proton research project. What is that? Well, stay tuned. I will be posting that to you next week. But this used to be a case study, and quite honestly, I don't know about you guys, but yeah, we're going to do a research project instead. So these are how the points break down. As with previous courses, you must receive a grade of a 75% or higher on the final exam to get a passing grade. If you have a question about the grading, here is a link that works. I checked it the other day. So I'm not adding any more books or anything like that. What the con planning book is fine. I will provide you with some supplementary materials. So you need not go out, and there are a couple of textbooks out there. Quite honestly, the cover is the best part on a couple of them. Extremely physicsy. So, and it's just, I'm not discouraging you if you have that desire to dig that deep. Go for it. There's certainly no shortage of information, but for practical purposes, I'm paring that down to a couple handouts. So please participate. It's just more fun that way. Don't share your work. There is an affirmation of inclusion. You will always be free from harassment, discrimination, and we want feedback. If that is something you do not feel you have received, courtesy of myself or one of your classmates, please visit the link to find out what your options are. As I said, cheating, stealing, plagiarizing, anything like that is violation of the Bellevue College Student Code. If you don't believe me, feel free to check out the policy. Let's see, what else do we have? Computing services, I think is it's great, but I think for those of you who are remote or online strictly, I've always wondered, like, that should be a challenge. You should feel like perhaps you are discriminated against because I'm offering you Bellevue College specific academic help. I'm sure the school might say, well, they can fly out here and use the services. So I guess that's an option. But let's be honest. Disability Resource Center. If not so much if you have something happening to you now, but if something were to happen, there are resources available, whether it is both an emergent kind of situation, but bottom line, the school, and namely myself, will be happy to accommodate any such unplanned or unforeseen emergency. Public safety, for those of you who do come to campus, public safety is available 24 hours a day, 7 days per week. This is the phone number. They are all over the place on campus. So please use those if you are taking a later class or you, as I was saying, in case anybody missed it. So my Wednesdays might be kind of pulled as far as having the day off per se. So if I do start needing to leave from one of the clinics, I may be teaching more from the college. So if that does become a thing, I will update on the module for that day if I'm going to be on campus. Okay, that would be kind of my notification to you, so that if anybody's in the area and they want to come to the school and watch me live, have at it. Regarding religious and faith accommodation, this is one of the new ones. Washington State has implemented that reasonable accommodations must be made for reasons of faith and conscience. So if you are, as we head into, this particular quarter is always one that it kind of crosses over into holiday season and all that, in an effort to make sure that nobody is missing anything or feels like they are not given their proper time to pursue their amendment rights for religious freedom, then you have the option to pursue a couple of avenues. So there are policies here that are outlined. However, in order to make arrangements for anything specific to this class, in following with the policy, if there is an exception, and really what we're talking about is for like the midterm, the final, any particular class day, if there is a religious or you have some kind of a faith or conscience that precludes you from attending class or taking the test on a certain day, you must file a request and it must be submitted within the first 2 weeks of the quarter. So if you need to have accommodations made for a different testing day or what have you, please make sure you fill out that form. These forms, once completely filled out, are essentially rubber stamped with approval, at which point I get notified through the school and to work with you on trying to rearrange whatever schedule needs to happen. So feel free to utilize those services. Again, I put the links down here in case something was problematic. So our final exams are scheduled for December 4th through 6th. As before, you guys should be used to it by now, the mechanism by which you have the take-home, online, and oral exam. If you need any questions as far as what the academic calendar looks like, feel free to hop on over. There are deadlines for anybody who is going to withdraw from either the course, ultimately then the program. Once you have read through, and if you have any questions or concerns or anything like that, this is the standard form. So you can put down your questions, sign a date. If everything looks good and you understand and don't have any questions, this top one, just sign and date, and you can electronically send that to me, and I don't need you to print it out, actually physically sign it and send it back. Just the email with it attached is all that I need. Okay, so this week it's going to be a little bit overview of the whole course. We're going to talk a little bit about interactions with particles. We're going to talk a little proton, a little neutron, a little heavy particle, just as here's what we're going to be doing. Online this week, there are a couple of, there's really just one recording. It is derived from physics presentations you might have been exposed to before from MD Anderson on basic atomic and nuclear structure. If it is difficult to hear or anything like that, there's a transcript that goes along with it. So you have the written portion of it. Couldn't believe that the school has a student environmental responsibility piece. Oh, yes. There's a big push for that. I think, yeah. What is it called? Climate justice? Environmental justice? I think it's like it's actually a new course of study. Anyway, so I've also put up here some focused topics and some notes. So what am I talking about when I talk about focused topics? Well, so this is in essence what we will need to cover this quarter. At some point in time, we will talk about darn near all of these. So when we get into electrons and starting in week 4, 4, 5, 6, and 7, I think, these are all the things we're going to be talking about. When we talk about total skin, this is what we're going to be talking about. You know you're big in the world when you have your own technique, right? If you're going to Stanford or MD Anderson, they name the technique after you. Like you've done a few of these. And then protons. This is what we will be talking about with respect to protons. Now, since you just did the QA class, was there any discussion on particle beam or special procedure QA in that particular course? And long time ago. Well, if not, good. But if you did, great. If not, I will be providing you with some of the QA material. But I've also put up here some notes that I would like you to make sure that you have. Now, part of these, you're going to notice there's a lot that overlap with photons at the beginning, as we talk about even tonight. And the reason why there's a couple reasons. One, because electrons and photons are rather intimately related. And B, because it's probably been a while since you guys have talked about anything related to physics stuff with particles or photons for that matter. So a way to kind of, again, bridge the gap back into all things school related. So this is always interesting. The synchrotron and cyclotron we'll talk about when we get into the proton piece. But tonight we're going to talk a lot about charged particles. There breaks up into light and heavy. Basically, light is anything just electrons and positrons. Heavy is anything other than electrons and positrons. There is a tortured range that electrons or charged particles take of the size of electrons, whereas compared to these heavier particles like protons, those things tend to travel in a straight line. So these particular notes with respect to how things interact is important. Then we get into, as we start to get in a little bit into neutrons next week. So how it's going to go, what this looks like unfolding is this week it's live. The next 2 weeks are only online. So let me say that again. We will not meet again until, drum roll please, 1, 2, on October 9th will be the next time that we meet live. The next 2 weeks are online only. They will be unlocked probably within the next couple of days, so you can get a real good head start on all things dosimetry 331 at your own convenience. And yes, Chris, I think you could probably teach this part. And this was something that Sharon Hummel did a couple years back. So she does a really good overview of neutrons. And yeah, it's a nice, well done set of presentations. Okay. Any questions? So you've got some notes. You've got kind of the broad overview of what we're going to be talking about this year. The syllabus is the only assignment you have. Your homework, so to speak, is to send in your signed syllabus. You have an online recording, physics-y, but easy to follow physics. There's a transcript here in case you can't hear some piece. And then there's some sample concept test questions that have the answers with them, so you can kind of test yourself. All right. Any questions? Anything at all? Like, how did the Huskies lose to Cal? Like, have you ever seen a lightning storm like that? Nothing? All right. Fair enough. Well, let's get into it. So I think as you settle back in, this might be exactly how you process tonight, depending on how what you take away from this particular discussion. So if I just say your name randomly, maybe that will help. So as we said, there's a couple things that we need to make sure that you know how to separate, because there's I think a fair amount of time there's confusion when we talk about interactions with charged particles in and around the focus being on production of X-rays. We use charged particles to generate through Bremsstrahlung interaction. And then you get into like, well, in a photon interaction, does that do Compton? Because there's a Compton electron, or the photoelectric effect. There's some stuff like which one goes with which. And I think there's always been this kind of vagueness if you don't have it really well hammered out. So anytime we're talking about electromagnetic rays, we could probably substitute that term as photons. There is a well-established, although it's only been in the last 100 plus years, I mean, relative to human history, it's relatively recent, where photons can behave as particles and as waves, where we can imagine if we drop a pebble in a pond, you can see the ripples come out like waves. And yet at any singular, if you put, kind of slits in the water and a single photon, or ripple passes through that very small slit, it tends to behave a lot like a particle. And so there is all sorts of neat and interesting stuff that has gone in over the years between classic mechanics and then our famous Einstein. So if you were to unleash this massive amount of, electrons, generating X-rays, all that good stuff, you would get refraction. You can get a reflection off of a wall, anything that interacts with that material, so you can act as a wave when it leaves this magical box containing all things photons. And yet when it strikes a small point, or here, it tends to behave like a particle. So the only way to kind of explain any of this had to do with Dr. Einstein's theories that kind of summarized everything in terms of it using his photoelectric effect. But what he explained was that there was really kind of this particle wave duality, that the size of also what we're talking about when we talk about some of these particles, it really is a law of scale. Some electrons themselves, for example, are very small relative to their counterparts, a proton, a neutron, a helium nucleus, what have you. So we should know the difference between X-rays and gamma rays, right? That shouldn't be something new. If you recall that they are the exact same in terms of what emanates from a particular place that is pushing those out. You couldn't tell, in other words, if you were standing away from a radioactive source or from a machine, if your back was turned and you just were exposed to it, your body wouldn't know the difference between a gamma ray and an X-ray. It all has to do with how they're produced. Gamma rays originate in with a natural source, not via things like Bremsstrahlung of charged particles interacting with the nucleus. Ionizing radiation is something that we use a threshold. Really, when we're talking about ionizing radiation, we're talking about photon energies greater than 1 keV. Shielding for these guys is done by high Z materials, so lead or depleted uranium. Then we get into some of these lighter charged particles, and those include electrons, beta rays, and positrons, which is kind of a, positively charged electron, if you can believe it. These guys, these guys lose a ton of energy, ton of interactions right when they start to interact with whatever it is they're passing into. These guys, because they're charged, have a very well-defined range that they're going to go. So what does that mean? That means, unlike photons, if you were to look at a photon beam, here's a magical question. If you were to treat somebody right and left lateral whole brain, what is the most likely outcome of interaction for the photon going into the lateral brain field? Does anybody know what is most likely to occur in that situation? Because it's probably not what you think. So in reality, what it's really asking you is, what is the comparison between, let's say, a photon beam and a charged particle beam in terms of the propensity to have some kind of interaction? Well, photons or anything, like them, but certainly on any kind of a whole brain field, a majority of these things are going to pass through and not do anything. They're just going to pass right on through where it is we're treating. So the highest probability is that a photon's not going to do anything. Now, it is impossible for these guys to pass through anything without going and working through some interactive process. And because they give off now, unlike photons, which we can kind of define in terms of, we talked about fluence a lot, whether it be an IMRT where you're modulating the fluence. What you're really doing is you're modulating the number of events that are able to take place. You're limiting the number of photons when you put in an MLC leaf or a lead shield. So you're reducing the count of photons when you do that. That is unlike what we talk about with charged particles, where we talk about those lose energy. Not so much lose their quantity, but they lose their quality. So because of that, and because they abide by this generalized kind of instant, it's kind of like instant torque in a Tesla, right? Or any electric car. It's instant start interacting and interact all the way until their energy can't deliver anymore. So they behave by what's called the CSDA, or continuous slowing down approximation range, CSDA. So for example, when we treat with somebody with a 9 or 12 MeV electron for, let's say, a breast boost or something like that, it winds up being about a couple centimeters, such that at 8 centimeters or 12 centimeters or 15 centimeters away, there's nothing left. You're not seeing a bunch of electrons make their way that far. Then we get into some of the big guns, where you take protons, and some of the more famous sites for those, Mass General, Loma Linda, we have them all over the place now in the country. If you're not sure what a proton is, there's a link for you. Pretty entertaining. Some of the take-home things related to protons and electrons, these guys are about 1,800, 2,000 times, but really about 1,800 times the mass of an electron. Because of that mass, anything that's that heavy, they're going to travel almost straight up in a straight line, right? They're just a gigantic garbage truck going through, and there's not a whole lot that's going to steer them off their path. Now, as they start to, remember, charged particles give up energy. They don't give up necessarily count. So at the end, but little bits and pieces kind of get picked off as they're working their way along the beam path. And it's at the end of their path that they give up all this energy in the form of all these interactions take place. They slow down, they're big and heavy, and you get this spike in dose right at the end of that range. And so in protons, we refer to that as called the Bragg peak. How do you stop these guys, these protons? Well, you can unplug the machine, or you can just shield with medium Z metals to get yourself, provide a nice healthy bit of electrons, which, because these guys are negatively charged and protons are positively charged, they kind of cancel each other out. So high Z materials, though, unlike shielding for photons, there's a difference between an R and an H. High Z materials should be avoided because that's what's going to produce those secondary X-rays and neutrons. So let's say we want to take all the benefits of these big, heavy pieces of particle and a proton, and we say, boy, it's really nice to be able to just blow out a tumor, just absolutely lay waste to it. So wouldn't it be even better if we could take and put a couple of those things together and actually split off the nucleus of maybe a small atom and create these kind of what's called alpha particles? And so we look at these things as being kind of packaged up very nicely. Alpha particles are oftentimes given up by the decay schemes that you're going to study when you get into brachytherapy. So what's interesting about these is because these are so heavy, you can stop them with just a piece of paper. If there's an alpha source that we're sitting on your desk right now, just put a Kleenex over it and it's going to stop. But the number of interactions, the amount of dose on just the front end of that Kleenex or that piece of paper, very high. So if you ingest or you inhale alpha particles, that's a problem because they will absolutely destroy things like lung tissue. Beta particles, now they are charged too, but they're super light. So because these are charged, there's a finite depth, but they're so big, they kind of, they don't have the oomph to get past anything. Beta particles, a little bit smaller, they can kind of slip through things, but they're going to stop pretty quickly. Then you get to gamma and X-rays, which are going to hit that lead piece. And then we get to this kind of no man's land, right? The mighty neutron. And neutrons are interestingly a lot like photons. If you were to look at a neutron beam dose profile, compare that to like an 8 MV or 6 MV percentage depth dose or dose profile, they're almost identical, right? Because, and think about it, what's the difference between these two? Well, this has no mass, this has mass, but they're both they're not a positive or negative charge, they're just neutral. So the difference that exists between these two is a function of, yes, they are both neutral, so they can pass through things. They're not going to be inspired to stop and look at the equipment around the shop because they're on their way somewhere else. But these guys have so much, they couple it with mass and they don't stop and smell the roses. So they're like the bowling balls going through the pins, right? Every piece of dust that's on the floor of the bowling alley lane, right, is the bowling ball is just going right over those. It doesn't care. When it starts to hit something that has some meat to it behind it, that's when things start to go awry. So anytime you take any sort of a particle like alpha particles, or you hear these, people have been treated with all sorts of, argon, any sorts of heavy types of particles, what we can all just kind of mentally picture is they're going to travel a lot more slowly only because of the protons, comparative mass. And so because of that, they give up their energy, even though they have the same energy, the mass kind of slows them down so they don't have as much of a range. These have been used in treatments. So how do you stop these guys? Well, if you just have some spare paper. Low Z materials, you just need something, really anything to stop. Okay, so we talked a little bit about those neutrons, and what you're going to hear over the next 2 weeks, certainly, is what happens when you have neutrons that are incident on a patient. Well, in that case, neutrons are going to, because of their size, right? Think about it. You have these tiny, tiny little things circling around the outside, these orbiting electrons, right? And the difference in mass is so much greater that even if an electron happens to come across the path of the neutron, it's not doing anything, right? The neutron's neutral, so it can't interact on a Coulomb force level. What you're left with is simply, it's just going to keep going until it runs into some other big things, namely protons and its brethren in the nucleus, the other neutrons. So primarily, they're going to interact with colliding with protons. In a hydrogen nucleus, and like we're all made up mostly of water, so hydrogen is a great interactor with neutrons. So you can, and anytime you have a photon beam, when you dial up anything higher, what do you guys know what the threshold is again? What energy do we start to be concerned about neutrons in our photon plans? Who recalls? One guess for 15. Yeah, 10. 10. So 10 is when you would start to see the presence of them. Obviously it's one of the reasons why though you don't do 15 or 18x IMRT or VMAT. So when you look at how these things interact, they do it kind of two different ways though. So you're going to hear these terms that get floated around where there is elastic and inelastic scatter. So anytime we talk about some of these interactions, where you have some object that interacts with the nucleus, only a couple things can really happen. Whether it's a neutron, a proton, an electron, but there's going to be some scattering event. It might kick out something. But the sum total of the energy, what happens to that? So that's what you have to follow, is the energy coming in and the energy going out. At some point, if you have a neutron that comes in and it doesn't eject a recoil nucleus, the energy that takes place in the transfer of the direction from here to here is a lot like Bremsstrahlung. So even though this is not a charged particle, the mere fact that it changed direction, the extra energy that it releases comes in the form of a gamma ray. All right. So with review, electrons, right, that reside around any nucleus have energy called binding energy. And in order to knock one of those things out, something has to have an kinetic energy that is at least as high as whatever binding energy it is for the electron to be kicked out. So if it just has minimal energy, well, it might kind of make the electron that it struck just kind of wiggle. But in order to, once you knock out that electron, then we get into this cascade type of event where you have other electrons dropping down to fill vacancies and photons are emitted. And this is something that we've talked about in the past. So the characteristic energy that is yielded in this interaction is oftentimes referred to as characteristic radiation, because you know exactly what energy is the binding energy by the energy coming out of the photon. And to the level that you can actually tell what a substance is by basically irradiating it and seeing what happens and measuring the characteristic X-rays that are generated. From those levels, the calculated energy or the measured energy, you know exactly what material it is you're hitting. So NASA uses those very same things when they want to know what is lying on the surface of some random object. They just impart a bunch of radiation onto it and measure what gets kicked out. So in excitation, there's not enough energy to necessarily kick out the electron. So the chemistry of the atom is essentially the exact same. But anytime you have any sort of disturbance in the force, the electron cloud geometry, that's when you might have some biological event. So ionization, this is what we live on. So when you have reached and moved past the binding energy threshold, electrons are going to jump down, fill the vacancy, we just talked about. In the grand scheme of all of this ionization piece, if you were to look at all the binding energies across all the tissue that you have in all the different shells, if you were to look at the average of those binding energies, it's 33 keV. which means on average, it takes at least a 33 keV incoming kinetic energy to eject an electron from an atom to ionize it. So X-rays and gamma rays, let's review a little bit the 5 ways that these things, so even though we're talking about particles, let's verify that these are not related to particles, okay? These are X-rays, gamma rays, all that good stuff. Coherent scattering, low energy, diagnostic, very small. We don't deal with that. Photoelectric, we do. Again, recall that it's a process that is much more likely to occur in high-Z material at low energies. The incoming photon, quote unquote, sees that innermost shell electron. 85% of the time, it's the K shell. And it gets absorbed in that process. Depending on the amount of energy coming in and the amount kicking out, you can either knock out the electron, it can jump to another shell. If it's ejected, it's called a photoelectron. And that little electron in this process can go out and it can cause biological damage. As we talked about before, that vacancy now is filled with generating characteristic X-rays. Sometimes these things, these X-rays that are generated from characteristic ionization, they might get immediately grabbed and absorbed by the same atom's electrons. It actually happens quite a bit. And if they have sufficient energy, they can actually eject another electron in this second ionization event. And if that gets ejected, that's what we call an Auger electron. And that oftentimes will be ejected and goes out and does some biological damage, leaving the atom to become essentially a free radical. It's going to have a net charge differential if we remove one of those valence electrons. And that has chemistry-related impact on the cell that we're treating. Compton is what we all know and loved. It also sees, these things all have eyes. It sees, Compton, the outermost valence shell electrons, and it really just kind of, it hits them. And recall that these electrons have very low energy, binding energy. The further away from the nucleus you are, the less the binding energy is. Now, in the process, this Compton interaction, it's the electron that goes on and creates the damage in the tissue. It's about 75% of the damage comes from this electron spit out by the Compton interaction. That leaves, you now have an atom that's minus an electron. So it becomes a free radical, also causing this biological damage. And that accounts for about the remaining 25% of the other damage. As we know, probability of Compton interaction is inversely proportional to energy of the incoming photon. What does that mean? That means as you increase energy higher and higher, you lessen the likelihood over and above our treatment energies of the probability of interacting via Compton. But the good news is that because it deals in the outer shell electrons, it's independent of the atomic number. So that's why we see horrific MV images versus when we look at diagnostic X-ray, if we look at Compton scattering, again, tends to be more forward peaked in treatment. But if you can get enough scatter, you can get a much better image like in KV. Okay, main effect, 30 to 30. Photodisintegration, this is something that happens, while it can happen, you know, this is all, guys, this is all probabilities, right? So greater than 7 MeV, but essentially if you have a very, very high energy photon and it deposits a whole lot of energy right dead center of mass in the nucleus, that thing is just going to blow up. And so you get a lot of neutrons that are spit out, but that photodisintegration essentially just goes in and blows up the nucleus and ejects all those compartment pieces outward. So for us at therapy energies, we don't deal a whole lot with coherent scattering. Photoelectric has a smaller effect in that we do see this taking place at the diagnostic kV range. Compton scattering also in the CT and treatment side. Pair production, again, smaller effect. We don't see a whole lot of it, but if you recall, pair production at the end generates 2 511 MeV photons and has photodisintegration, as we said. It's super high energies. No real effect is going to be something that we need to concern ourselves with. But what we do want to concern ourselves with are things that happen with electrons. So the same process that happened earlier when we described about like, hey, how do we generate X-rays? There's two fundamental things that happen when charged particles interact with matter. Okay, two things, which makes it kind of easy. For these electron guys, you're either going to get radiation via Bremsstrahlung, sometimes they'll call it radiative loss, where you basically bend the electrons around the nucleus, right? Those little guys are negatively charged, and the nucleus is full of positive charge, right? You have only protons and neutrons. The neutrons are acting like the glue because all those protons would, if they didn't have neutrons around them, they would all just fly apart from one another because they have the same charge. So it bends this negatively charged, is kind of, that's kind of interesting, slows down, looks at the nucleus, changes its direction. That energy that is shed off is given off as an X-ray. Or you have this ionization event owing to characteristic X-rays, as we talked about before, where you have a charged particle comes in, interacts with an orbiting electron, that electron gets released, the vacancy gets filled, shedding the energy as a characteristic X-ray. Any given electron can, in any single interaction, so it's a statistical probability, can either lose a very small or very large amount of its energy. And it can be scattered a very small or through a very large angle. So the reason why these lead to kind of a big variation on how far electrons can go, and why we don't necessarily see a Bragg peak associated with electrons, is because of all this variability. So how far they can travel into the tissue, the variation, though, that is a function of how much they can vary in their scatter angle and how much energy they give up in any given interaction, is so varied. So we call this term what's called range straggling. So because before I said, oh, the good thing about these things is they have such a predictable range. Well, electrons, they just don't pack all the same punch. So we have to kind of define that as range straggling. Protons, how do these things do? They interact with those orbital electrons too, but recall these guys are really big and heavy. And why do these guys interact? Well, Coulomb forces, right? They're positively charged. They're a real positive figure. They're coming over to those really negative, always down electrons and the circulating around. And they might just look and see that, hey, there's not very many of you, and I don't really have to stick around, so I'm just going to kind of scatter just a little bit and not really do a whole lot. But you're going to give up ever so slight amount of energy. But then as you start to go through more and more of these slowdowns, kind of slight scatter, over time, as these things start to slow down, that's when kind of that Coulomb interaction, that Coulomb attraction between the negatively and positively charged particles become prime time. So the slower the proton, the more energy it loses to the tissue's electrons in and around that. The region of rapid energy loss or high deposition of dose in the tissue is what we call the Bragg peak. The distance where that Bragg peak occurs can be very accurately calculated, unlike what we could say with electrons. When you guys do some plans with electrons, you'll find out pretty quick that sometimes these things are really hard to control. You look up in the table and you see, oh, that's the Dmax, it's 2 centimeters, and I ran it for 2 centimeters and it doesn't look anything like what it should. Yeah, welcome to electron planning. Protons, because of their mass, they overcome a lot of the shortfalls that do electrons find themselves in. So for Bragg peak, if you can find out where that's going to occur and control it, that is the perfect kind of premise for a radiation beam, right? Where you just put the tumor right inside that Bragg peak and you're golden. All this dose gets deposited right in the middle of the tumor. Are you kidding me? Now, protons very rarely interact with the nucleus, and that kind of makes sense. That's a net positively charged amount of stuff in there. Now, because though they are heavy and because they do so much interaction at some point in time, it's believed that protons probably enhance cell kill on the order of 10 to 20%. So there's this belief that there's actually kind of like a radiobiological equivalent of 1.1 or 1.2 over and above what photons can do. So if you ever looked at a proton, if you've ever gotten a plan from a proton facility, on that plan report or in a plan report for photons or protons, you're going to see something called CGE, which is cobalt gray equivalent, or basically photon equivalent dose. So when they report something like 70 gray with protons or 84 gray equivalent with photons. So protons carry with it their prescription doses might be less, or they might be the same, but what they'll find is that they should get better cell kill just from the very nature of how these things give up their dose. Now, if the benefit of going from a light charged particle to a heavy or a heavier, larger mass particle is good, well, then logically we might say, well, then let's look at something even heavier, right? Let's get some noble gases up in this thing, and helium and argon. Let's split off those nuclei and let's go see what they can do. So those things too have, similar path that protons do, and they even scatter less initially because they're even bigger, heavier, and they will have a faster dose fall off and a very large Bragg peak at the end. So with these guys, they tend to interact with the nuclei more often compared to protons. But at any time, they can lose a large amount because of their makeup and their mass. They could lose a large amount of their energy in any single interaction. A little harder to control those guys because they're so much bigger. But if you could, these things, just as you kind of scale up the mass part, as you increase mass, you tend to get at least a better biological effectiveness. Might not always be what you want, but it will carry a higher RBE. Now, as I said, because these neutrons are heavy, similar mass to a proton, but they're neutral. So they only will lose energy by interacting with the nucleus. But similar to heavy ions, leads to a sudden large loss of energy in a single event. So they have also a high RBE. However, they follow kind of the X-ray path of the dose fall off, exponential. And really that's just because these things are random. But unlike any sort of positive or proton ion interaction which increase with slowing velocity, these things just kind of follow the same, slow path. So that in a neutron beam, 50% of the dose is still at 10 centimeters. Unlike these other things. So recap: photons, indirectly ionizing radiation. Anything not charged, by the way, is indirectly ionizing. Remember, indirectly ionizing, they're what sets the charged particles in motion as they interact. So those secondary particles are what deposit the energy or give up the dose in whatever material. Now, sometimes, so photons don't give the dose per se. They're just liberating all these charged particles to do their dirty work. But photons will interact in 5 ways. These are the 3 primarily we want to pay attention to. Again, diagnostic, radiotherapy. The probability of interaction is given by a linear attenuation coefficient that is dependent on Z of the material, the energy of the photon, and the electron density of whatever it is you're exposing. So that's all fine and dandy. So electromagnetic radiation and its interaction with matter goes through all these things. Now, there's other things that it does, right? There's scattered radiation, there's secondary, all this other stuff that's associated with it. But let's come over here to when you're treating with particles, these things are going to ionize or excite due to the fact that they have a charged characteristic to them. Electrons are going to go through collisions. They're going to give up energy in the form of Bremsstrahlung and a radiative loss. They have a stopping power due to the electrons kind of natural, each one has its, in this tortured path, each one has its kind of view that it's not always going to subscribe to what would be predicted. So there's this idea of a total stopping power, which is just look at the cross section and kind of normalize everything at some point. But all of these particles, whether you're talking about electrons, but as you increase mass, then the range becomes much better defined. But we would define electrons, the range we could almost use is that term range straggling. Do electrons have a Bragg peak? Technically, any charged particle does, but we don't really associate electron beam as having a Bragg peak. They're just too small, too light comparatively. Scatter radiation, of course, that is something that we deal with all the time, and we can have scatter that comes from the machine, scatter that comes from the patient, from any of the equipment. Recall that scatter is a function of energy. So the higher the incoming energy, the more forward peaked it is. And I want you to recall that if you look at photons, as you lower the energy, right, you can have more and more scatter. In fact, you can have scatter coming directly back. You can have the same thing with electrons, depending on what it's striking, what kind of a surface it's striking. But it's no doubt, if you take, when we take an image or whatever it is that we're exposing gives an intensity pattern based on what it's made up of that we're exposing. Now, when primary radiation interacts with what we're striking, electrons can be produced, and those are called secondary electrons. Those are what's giving up the dose or giving the dose. If they have enough energy, they can go on and create their own separate track along the way called a delta ray. Delta rays often don't deposit energy in the immediate vicinity. They kind of get out of their space and go do their business. So it has some consequences of determining what the absorbed dose is in that point if there's a high percentage of delta rays occurring in that exposed medium. You will see that electrons, if you just follow the path of electrons, they, let's see, similar to your notes. These suckers, so there's the Bragg peak. They have already passed it. So an electron coming in strikes the surface, and it might bounce around, go back, go forward, over. They go through all of this horrifically tortured path. So we define the range as this, right? From where it starts to the last interaction. But if you actually took a measuring thing and actually measured the distance that electron went, it might be very different than what we calculated the range to be. So we have to kind of normalize everything and say, this is the only thing we can do. So we define our range as kind of but as some predetermined thing at the end, and they all tend to end about the same distance away. But it's not impossible to have some that go in a much less tortuous path, depending on the material that they're passing through, or some might have a much higher chance of interacting and scattering and all that good stuff, such that the range is less. So there's kind of an approximated range that we use. So this is what and so we might call this, if we had another same energy and it bounces over here and bounces over here and bounces over here, we might just take a line and say that's the range for this electron. And we would call that range straggling because events are happening in front of it and behind it. So as far as what happens also with the range is going to depend on, of course, what you're exposed to. So the range is going to increase as you increase energy, and it's going to decrease as you increase the Z, right? So if we go from fat to bone has the equivalent of the highest Z material, right? The range is going to be severely limited, even though comparing a 1 MeV to a 2.5 MeV, the range is going to be higher for a higher energy electron comparatively, but within the tissue difference, it's about the same. It's just kind of scaled up as you increase energy. So the differentiator is it's what this graph is trying to show us, is that it's a function of the density of the material and the energy, but the same generalized patterns occur. Fat is the highest range, then water, then muscle, then bone. So if we were to kind of summarize the amount of energy that gets transferred as these electrons are making their way, or any sort of charged particles making its way through any medium, we can actually look and see what's the density of that ionization track. So when these things interact with atoms, they're leaving behind ionizing events. So the ability for a particle or a charged particle to impart its damage is by leaving more and more of those ionizing events along its path. So we summarized that particular quantity of that objective valuation of how much ionization is occurring by the term LET, or linear energy transfer. Sometimes people refer to it as the restricted stopping power. While that is a great term to know, I've only ever heard of it in the clinical setting as like LET. So what is that? Well, it's always defined in terms of energy per unit length. The most common is keV per micrometer. So it is the amount of imparting energy over some distance. So what this is saying of this chart is that high energy, high mass is the highest energy transfer at for each keV per micrometer. So in other words, 1 MeV gamma rays, very little ionization track. There's going to be some because it's liberating some electrons. They're going to go out and do their thing. As you then bump up to 100 kVp X-rays, you get a much higher LET, factor of 12, and you've dropped the energy from 1 MeV to 100 kVp. So you dropped it by 10, and you went up in LET. Why? Because in this energy range now we have photoelectric effect, we have cascading, we have a lot of events happening with electrons that's helping increase that dose. What if we pull the energy even further down, and we're going to substitute, instead of X-rays, we're going to put in these electrons, beta particles, beta minus particles are the same thing as electron. So a beta minus is akin to an electron the way a gamma ray is akin to an X-ray. So 20 keV, so you're going to increase your LET because these are charged particles. So you say, all right, well, what happens now if I go way up in energy? Well, I should drop, right? This was 1 MeV gamma rays, so I should drop, except there's now mass to these guys, the neutrons. So gamma rays, a 5 MeV gamma ray isn't going to produce the same as a 5 MeV neutron, only because the neutron has mass. So the highest energy with the alpha particle, heavy, 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 it gives the highest linear energy transfer. So energy lost by the radiation as a function of the length of track that it's creating. So the take home, radiation that is easily stopped and yet has a high LET, that's probably the stuff you don't want to ingest anywhere. So what do we see clinically in the difference? Well, if you were to run a plan that had a beam, an LPO beam of some kind that exited into the eyeball, that would be a problem on a photon field. Most physicians would not like to see this particular beam. On a proton, because you know what the range is, you can use that exact same angle, but just choose an energy of the proton so that the dose is all delivered right in here, and they just stop. So there's no dose, right? Charged particle, there's nothing at the other end. It's like having the perfect wall or a shield here. They just stop. So charged particles lose their energy, very different than X-rays, gamma rays, or don't forget, neutrons are the same. So even though we're going to talk about neutrons, think of those, the neutral, and they are just like the X-rays in a lot of ways. Charged particles are surrounded by this electrostatic field, this Coulomb field. So they are going to interact with electrons or nuclei, if they're positive or negatively charged, accordingly, of every atom they pass. Why? Because every atom they pass has a negative field around it and a positive central core. So if a charged particle has either charge, they're going to find some sort of attraction to one or the other sections. The force between the two particles is proportional to the Z of the material, the energy squared divided by the radius squared. So what does that mean? That just means that the attraction between the charged particle is going to, as the energy drops, and the range is a function of range, so that we see this in the Bragg peak. As the energy starts to drop, that range really collapses down and all the dose falls right in that Bragg peak, and then it drops off. What's the probability of a charged particle passing through a medium without interaction? It's 0. As I said before, what was the most probable thing that would happen to a photon in a lateral brane field? Nothing. 0. So big difference between charged particles and photons or neutrons. So an example, a 1 MeV charged particle typically will undergo 10 to the 5 interactions before it loses all its kinetic energy. Now, the mechanics of how these things give up their energy is a function of which path they go. So you can have a totally undisturbed, doesn't even notice this tiny little thing over here, or it's far enough away that there's really nothing that's going to impact. But in general, there's only one of two things that's going to happen. If the trajectory of the charged particle is close enough to fall within this range, you're probably going to have some sort of collisional energy loss. If, though, it's going to come into close to the nucleus or somehow bend around because of the charge here, that is when you get this kind of a radiative energy loss or Bremsstrahlung effect. So excitation. So if you get the electron energy is equal to the difference in energy between its own and the higher energy level, the electron level is excited to the higher energy level, and it's going to, so in this particular case, you might just have a passing charged particle. There's a little bit of an energy transfer. What happens then is a function of what is the binding energy and what's on the outside to fall in. But the bottom line is when this sort of happens, if it loses an electron in this whole thing, this is now becomes ionized. So transferring a very small amount of energy, even just a few EV, can cause ionization events to occur within the atoms, and that's kind of what we live for in radiation oncology. So if anybody's ever heard of Cherenkov radiation, it gives off this kind of bluish light. You see this a lot in particle energy that is the core of reactors, for example, because of all that time you spent, like in Chernobyl and looking through stuff. Fukushima, 3 Mile Island. Those are just really fun spots to take the family. Okay. When we are in the process of going through these collisions, when we have ionization events and we have delta rays, characteristic X-rays, Auger electrons, all of these things, we have to keep in check that the energy exiting and the energy that came in somehow kind of either magically balances, or we can track and see what actually happened to the system. So as we talked about before, characteristic X-rays are unique as a function of the Z of the material, such that you can expose any material with a charged particle, and the difference of as it breaks around and there's a characteristic event owing to the ejection of a K shell electron, an L shell electron, one of those inner shell electrons. But that is going to give up a very specific energy photon owing to the type of Z of owing to whatever the material is. That's why it's called characteristic, because it's characteristic of that material. So as we said, if you were to look at before the average binding energy for a person across all of those energy shells, it's roughly 33. So it's interesting that if you look at ion pairs created in terms of just across all kinetic energies of stuff coming in, the mean number of ion pairs formed when all the energy is used. For air, the ion pair creation is 34 eV. So essentially, what we call the W, but the way to recall that, hey, the average binding energy is very similar to what it's going to take to create ions, even not only in you, but also in dry air. So 33, 34 EV would be a pretty easy way to remember that, look, overall, on average, this is what we have. How does that happen again? Incoming particle bends around, gives up a Bremsstrahlung owing to this change in direction, or you can have, again, the collision, characteristic X-ray, all that good stuff. But Bremsstrahlung is neat because that's how we build our X-ray fields, right? This is essentially what happens in your LINAC. Now, for electrons that are circling around here, the probability is proportional to Z of the material and 1 over the distance, or the closer. So these are always going to impact, again, typically is right near the nucleus. These are typically electrons coming in. This is a net positive charge. Up to 100% of that particle's energy lost comes out as Bremsstrahlung. However, there's really kind of a spectrum of energies that this might have. As we know, as we talked about, something you need to keep in mind. So the differences in masses between electrons and all other things. Electrons, those interactions are different from other charged particles because of its size. The mass of an electron, 9.11 times e to the negative 31, versus mass of a proton, 1.67 e to the negative 27. So it's about 1,800 and some change times larger than an electron is a proton. So what does that mean? The effects that we see are relative to only changes in energy and the angle that these things come in. And they achieve very rapid deceleration owing to Bremsstrahlung. This ability for us to look at how quickly a particular particle is going to, and where it is going to stop. So what that measures, the stopping power of a particular particle, is a function really of how dense that ionization is, the LET essentially. So as we said, usually in a particle's path, like a proton, it usually reaches the maximum called the Bragg peak shortly before the energy falls to zero. So there's this kind of continuous slowing down of these charged particles until they almost are out of energy. They give up all their dose. So an electron isodose set of curves, we'll notice that there are a couple of factors that we will need to explore this quarter. When we look at electrons compared to photons, we'll notice that unlike photons, electrons start out with a relatively high surface dose. They quickly reach Dmax, and then they essentially have a very steep fall off, at which point we don't see any more of them after a while. So there are characteristics, though, of this curve that you will need to become familiar with. The R100, or we reference things to Dmax almost exclusively. So no normalization to isocenter or a calc point or something like that. It's to Dmax for the beam. We need to know what the range for the 50% dose is. We're going to learn about this thing called the practical range, which is an extrapolated extension of the downward slope of an electron beam, where that intersects the percent depth, where that intersects on the depth side, gives you what's called the practical range. And there's some rules of thumb to apply to learn what that might be. And then you have an X-ray component that can occur. So we can compare and contrast different energy electrons and plot those out on curves, and we can see some very large differences as we change the energy around. Then when we compare that to, let's say, a photon and a proton, so photons, we might get a low entry, but we build up just like electron, but then we slowly drop off, such that 50% we're 10, 15 centimeters away. Now, if we just look at a singular proton energy, what's called just a native proton beam, so we're not manipulating the dose at all or the beam at all, we'll notice that has a very low entrance dose, right? It's giving up some, but right at about the time that it gives up all its energy, it spikes up in dose and then drops. So how is it different than when we start to make modulation of that proton beam? Well, as we'll talk about this quarter, you're going to see what happens when you make changes through compensation, through manipulation of the particular proton beam itself. What that does is it increases the surface dose and spreads out the Bragg peak. In fact, that's what we call it, spread out Bragg peak. Scattered radiation, secondary electrons, this is what causes, there are sources of scatter, and actually we generate scatter from our photons. That's what delivers the dose is via the secondary electrons. Charged particle interactions combine either hard or soft collisions, depending on where they originate. They can cause ionization, excitation, they can yield Bremsstrahlung X-rays. So we have these things called collisional losses and radiative losses. Collisions are ionizations or excitations. Radiative are Bremsstrahlung. We talked about a little bit about stopping power and what goes into stopping power. Right, when we come back to it's there. So stopping power primarily is going to focus on that point, which when we're looking at the range of any one of these particles, be it a proton or whatnot, we can accurately predict where this is going to happen based on just a nominal energy beam. So we have the ability to predict. What changes the ability for this thing to fall right here, though, is a function of the energy coming in and the materials that it passes through. So in order to be safe, they have to build in margins on proton plans to pass through things like the hips and all that good stuff. So hadrons, we'll talk about kind of in vein with protons. So these are those things that generally are experimental. So examples are the mesons or pions, where they're almost looking at subatomic particles to make up for exploration into treatment. So as we know, protons, neutrons, they're composed of these smaller elements called quarks, antiquarks, gluons. Hopefully you can't see those. We have some, but hadrons in general are referring to all this tiny little stuff that's subatomic. So how do you make these things? Gigantic machines. So there is colliders that you bombard. You can get huge energies on the order of you accelerate some particles 1,500 tera electron volts before you slam them into a substance. You could use hadrons to expose like uveal melanomas. Most of the energy, because these are sometimes they follow the same path as charged particles, like in terms of quarks and whatnot, you have no dose beyond. Obviously, then you get good tumor coverage, but really good sparing, as long as you can get it to where it needs to be. So when we talk about neutrons, recall that these suckers are, like I said, almost as big, just as big, really, in all intents and purposes, as the protons, but they have no charge. So they follow the indirectly ionizing radiation path. Here's a fun little tidbit. Neutron's half-life. So when you go and you treat somebody with IMRT with 18X, the neutron half-life is a little over 10 minutes. So in yesteryear, when people would go in and exchange like compensators or blocks right after treating somebody, really high, lot of MU, whatever, maybe it's a high dose per fraction, the therapist would walk right in and take the hand block off of the tray. Maybe it was like a hand block for an electron or for a thyroid or something, larynx block. But that was not a smart choice. Right? Those become activated and it's radioactive for a while after the beam is off. So there are neutrons running all over the place, which is why your physicists try to do their darndest to paint a lot of hydrogenated doors and walls and all that stuff to really, because these suckers bounce all around and you need something to absorb them. So there's a couple different types of neutrons, and they're designated by their energy. So low energy are called thermal neutrons. High energy are called fast neutrons. So in truth, all neutrons that you use for any sort of a treatment thing are fast neutrons, and then they slowly lose that kinetic energy. So to get thermal, you start out with fast and then you degrade the beam. So how do we get these things? Well, you can just have isotopes spit them out for you. Neutron generator. You can collide, things into one another, like using the Large Hadron Collider. And how do these things interact with matter? So they often follow what's called this billiard ball type interaction. So you have elastic scattering and inelastic scattering. And then boron neutron capture, that was something that people did a long time ago in the brain, and I hear it's starting to come back. But anytime when you want to break out and see what elastic scattering is versus inelastic, so incoming neutron jumps into the nucleus, the neutron gets deflected and it loses some energy. That energy is given to another nucleus that it interacted with, and that gets shot out. Now, this nucleus, the recoiling neutron, all this becomes unsteady, right? And so this thing coming out can go on and do other things, can bump electrons, all that stuff. But in this process, the energy coming in is equal to the resulting energy loss of the neutron as it changes its path and what the recoil is ejected. So the sum coming in equals the sum going out. Okay, we're going to follow the conservation of energy and momentum. Inelastic is when there's kind of a stopgap, like they're on the dark side of the moon. Okay, the incoming neutron comes in and it kind of just like stops for a second. It gets captured. Then it is re-emitted with less energy. And so the nucleus is kind of left in this, it has this extra energy just kind of sitting there waiting. So how does it get rid of it? It emits a gamma ray or another charged particle, which goes on to deliver dose. So the interaction probability, so as you increase neutron energy, you increase the target size. So when we talk about energy given to some nucleus and the amount that it's spitting out, it's, as we said, the balance being the energy coming in is equal to the energy of the neutron after the collision and the energy of the gamma ray that's emitted. Neutron capture, if you have some sort of material that you could inject into a tumor, for example, that really like to absorb neutrons, where you could take and you could surround the tumor with, some kind of that substrate. What you would take advantage of is the fact that you could irradiate with slow neutrons, kind of thermal neutrons, and it will come here and it will actually change from sodium 23 now to sodium 24, and it spits out a gamma ray. And that gamma ray is going to go off and do the damage. So it's kind of like you're using this material to get the gamma ray produced inside the body. So you're kind of creating almost like a target, if you will, using neutron capture. All right. Neutrons look eerily like an 8 MeV photon. This is the neutron profile. Crazy difference. Good tumor killing. Tissue damage is primarily by those nuclear interactions. Neutrons are high LET radiation. They have a high biological equivalence. Much lower chance of the tumor repairing. You can get away, therefore, with having a lower dose requirement. It's good for radio-resistant tumors. These suckers are so big, they don't care if you have oxygen. They don't care if you have a whole lot. They're just going to wreak havoc on everything they come into contact with. Know the properties of, obviously there's positive charge, know the mass. The proton half-life, if you happen to create them in your garage or anything, 10, 35 years. So these guys are around for a long time. How do they interact? Electronically through ionization, excitation, or on the nuclear level through Coulomb scattering. Recall that protons have a Bragg peak. And we're talking on the energy side, these things are much bigger, much higher energy than what you can get with photons. So 190, 250 MeV is not uncommon. Protons, very good dose distribution, low entry dose. Most of the energy gets deposited at a predetermined depth. And like I said, no dose beyond. They're all over the world. This is the kind of a current graph in the curve, and it's going up. Heavy ions, anything that is heavier than carbon, we could coin as heavy ions. They are composed of hadrons. Heavy ions refer to atoms that are generally completely ionized. So they're just the bare nucleus. You can point them at a target, or you can split them into two beams moving in opposite directions, and then you collide them at a well-defined spot for research. There have been experiments with carbon, silicon, all of these things. Pi mesons, there are some symbols here. They're the lightest of the mesons. I mean, of course, which kind of stands to reason, right? Because if you eat more pie, I guess you'd be lighter. I don't know. They're inside the nucleus. They're subatomic particles, so they follow the strong nuclear force. Pions are what hold the nucleus together. So they are essentially what strong nuclear force is what kind of overrides the Coulomb force. So even though all those protons are stuck together, the pions are what actually hold everything intact. They don't live long. That's true. 26 billionths of a second. But if you could extract them for treatment, here's what you would get. And this has been only done in very sophisticated labs. In dosimetry studies, you've treated monkeys and rats and all sorts of animals. In terms of patients, I don't know that they have, they've treated people with it, but I don't know what sorts of results they have had. But effectively, because it's so damaging, again, these suckers are small, right? So kind of falls under the burden of like the electron, but they themselves, they're almost so small, they're like lethal. They get in there and they do things much more violently than do the bigger, heavier stuff. So they get in and just absolutely destroy things. So the effective dose of these, because they do such a wonderful job blowing up everything inside, is the effective dose is much higher. So you can see here's our dose fall off, but we don't give anything with these heavy ions. And then if you were to go one step further and say get the subatomic piece out and use that for treatment, you'd have a very different outlook. So low LET, hadrons, protons, and photons. Similar RBE, but protons have a sharp dose fall off. So when we get to that point about RBE for protons, just know that it kind of depends on where you look. So when you're talking about RBE for protons, it's much lower than photons if you're looking in the beginning stages of the beam. Okay, it's low dose compared to photon. But at the peak of the Bragg peak, it's much higher than photons. So the balance is 10 to 20% biological effect. High LET, neutrons, heavy ions, pions, those suckers have high RBE, really good at killing tumors, and really poor at allowing for cell repair. If you want your cells to repair, don't use these things. Okay. So charged particles, photons, neutrons. Charge, no charge, no charge. So you should really know a couple things. So continuous interaction, continuous slowed down interaction. The CSDA, you need to know that those are attached to charged particles, not photons or neutrons. Which ones have a Bragg peak? We only assign those to charged particles, not photons, not neutrons. Photons have an infinite range, whereas charged particles and neutrons have a finite range owing to their mass. Okay. No rest mass, mass. All right. Finally, what is the difference between a physicist, an engineer, and a mathematician? Engineer walks into a room, sees a fire in the middle of the room and a bucket of water in the corner. He takes the bucket of water and pours it on the fire and puts it out. Physicist walks into a room, sees a fire in the middle and a bucket of water in the corner, takes the bucket of water and pours it eloquently around the fire and lets the fire put itself out. Mathematician walks into a room and sees a fire in the middle and a bucket of water in the corner. He convinces himself there's a solution and he leaves. So while that one really, I would tell you a good chemistry joke, but all of the good ones are gone. So, weak sauce, I'm sure. So as far as this week, I would highly advise you to focus on all things that are in your notes, starting only, helps if I can close this out. Why is that popping up? Okay. Technical difficulties. So I really do want you guys to know these pages, what happens, what is LET, what does it represent, happens to electron interactions. And I'm not saying you have to know it like because there's a quiz or something next week. I'm just saying we're going to be talking about this stuff over the next several weeks. So if you can get a grasp on some of it ahead of time, it will only help moving forward. Okay. But this is a gist of the deeper dive into all things particles. Any questions? You mean the new dosimetrist? So next week, no live class. The week after, no live class. On October, I think we counted it out. October 9th, we will resume. So the next 2 weeks are on neutrons, courtesy of previously recorded lecture. The material is will be posted. She has some homework. There are PowerPoint slides and the recording. So they kicked out, just FYI, they kicked out Camtasia recordings over the summer. So a lot of the stuff I have, and also Chrome is no longer supporting Flash. So I did pull those Neutron pieces down. So I think I just need to upload the 2 weeks recordings now that I have them out of Flash version. So I will, like I said, either tonight, tomorrow, but very quickly thereafter, Neutrons will be opened up for the next 2 weeks. You guys will have access to at least the first quarter of the course. When we come back on October 9th, you will be starting in electron beams. So I will be posting some not reading material, but some notes again for you guys to focus in on with regard to what we're going to be talking about. So look for that in a couple weeks. And other than that, there will be a quiz on neutrons. So after this, I will email you guys all the details, but there's a quiz on that section, so to speak. But that's it. Other than that, you have just one online recording thing to listen to. And welcome back. I missed you all. And I know that while that feeling is not mutual, I'm glad that some stability in Wednesday evenings will return to all of us, I'm sure. So I bid you well. I hope you guys get settled back in the clinic. And in the meantime, if you have any questions or anything like that, I'll be online for a while. But all than that, you are free to jam. Have a wonderful couple of weeks, guys. Enjoy, enjoy, enjoy.